All right. Thank you, everybody, for coming to our annual update from the Science Pipelines team. As usual, it is my pleasure to introduce the Science Pipelines team. We are the collection of scientists distributed across UW and Princeton and SLAC and other places. And we have the same goals as you. We want the best science out of Rubin Observatory. What we have in common is that we believe that our best way to pitch in is by writing the software that takes the raw pixels coming off the telescope, calibrates out the effects of the atmosphere and the instrument to produce catalogs and images to enable your science. We have a number of folks from the Pipelines team here in person who will be introducing the various algorithms. We'll be talking about what the current performance is. This is as we have done in the past, this is going to assume that people know the baseline plan of what the pipelines were trying to accomplish and what the goals were. So we're going to present this as a delta on last year, what has changed, and then current performance, known issues, and then how we plan on mitigating those known issues for next time, either when the alerts go back on Sky or for DR1. We have folks online as well who are here to answer questions. We're going to present this as an hour-long talk. Please hold your questions until the end. We're going to use Slido, which has a bonus of allowing you to submit anonymous questions. You can also sign your name if you want this to turn into a conversation. But it also means that you will have to type it in. So when you're watching this talk, and if you have questions and curiosities, please write it down as soon as it comes to your mind, because you'll have a place to copy and paste it later. The pipelines are constructed of algorithmic tasks. These tasks, you can think of them as building blocks for which we can construct the alert production pipeline and the data release production pipeline. These two pipelines share a lot of the same tasks. This year, this talk is extra fun because we not only have we seen the data at this point, but you guys have LSSTCam data at this point too, both through the alert stream, which has been live since February, which you can now access, where you've been able to access for a few months through the brokers. And also now you have early DP2. So we're gonna show performance from both of those data sets. So I'm gonna go a little bit into what data preview 2 is, since you're gonna be seeing plots from regions of the sky. So we were on Sky last year from April 15th and beyond. In those between April and the shutdown in October, we were mostly focused on taking images for validating the as-built system and commissioning the science pipelines themselves even though we had tested them on precursor data sets. For every new instrument, there's idiosyncrasies, and we have to optimize the pipelines for a new instrument. And then after the shutdown, we unleashed the feature-based scheduler. That was the cloud of points, the cloud of visits that you see in the northern fall region is all from this period of time. Sorry, this is gonna be hard. This period of time. The behavior of the camera changed a couple times in this time span, which led to 3 separate calibration epochs. That means that the calibration frames that you need in each of these epochs is different. And there's also a couple periods of time where there are no calibration frames that are of data release quality, and were not included for that reason. In query form, the query for data preview 2 looks something like this. There were about 60,000 visits taken total in this time period. Half of them were for engineering, AOS tests, pinhole tests, stray light tests. So those are all excluded from DP2. All vignetted images are excluded from DP2, and anything without a filter. RTN 111 has some tables with the fields that were covered, how many visits deep they are. The depth of the fields vary quite a bit. We have the field surveys from the beginning of commissioning, the first look era, and the early photometric and astrometric calibration. We then worked on this ecliptic stripe, and also we're hitting the formal deep drilling fields. The SV225 fields is one of our favorite. This was the one that went out with the survey start announcement as the so-called Ocean of Stars. This has 300 visits in each of the bands, which makes it really great for variability studies and just anything that you need really deep images for. You've been hearing a lot about the extended Chandra Deep Field South. I just noticed you can see the cursor on the back screen. That's better. Okay, so extended Chandra Deep Field South is not as deep as DP1 just because of the time of year that we were observing. Another field that you're going to be seeing plots from is Cosmos. Cosmos, we have 100 visits each, and we even hit it in 2 seasons in both May and December, which means that if you have any variability studies that you need a 2-season baseline for, this would be a good field for that. The mean full width half max in these coads is also pretty variable. Remember, this was commissioning data. We were not expecting to do any ground-breaking weak lensing with commissioning data. But it's also not bad. Like Cosmos, for example, has an average of one arcsecond full width half max. Something new in dp2.lsst.io is our data quality page. You can now go and pick some of your favorite metrics from drop-down menus and see them per tract over the regions that have been co-added. This is going to be beefed up over the next couple weeks with static plots that you can download, and also some. We're also going to try to do a full accounting of the data IDs that went into the processing and ultimately came out of the processing. So if you are notice that a data product is missing, you can go look it up on that list and see if it was expected or not. All right, I'm going to switch gears now and channel Lee Kelvin and background estimation. So Lee had a baby July 1st and is on paternity leave, which is why he couldn't be here today. Congratulations, Lee, if you're online. Okay, background estimation. So these are a few galaxies from NGC 4410 taken in 1994. 5 years later, this is from the SDSS, 1 magnitude deeper. From Pan-STARRS, another 10 years later, another magnitude deeper. And then you can tell where this is going. This is the EDP2 pretty coad HIPS map that you can pull up on the portal. And you can finally see in great detail all the interaction between the galaxies. There's also a very fun high proper motion star here. I will blink just so you can see it. Okay, so one question I already have gotten is why does it look different from the M49 first look image? There's a handful of reasons. Some of them are just cosmetic. The first look image includes U-band. The other reason is that in the first look era, we were given one directive, which is take this M49 data and make as beautiful a coad as you possibly can. Like, and this is a very different mission than take this pile of raws and make them into the most scientifically useful coad to get precision photometry from. So with just that mission, we took all the shortcuts we could. Like we turned the artifact rejection clipping config parameters all the way up because we had hundreds of visits and we could afford it. I affectionately call that configuration the PSF destroyer. We also added even after the usual background estimation that we do, we added an extra tract level background modification to match the bands a little bit better so that there was no like residual color in the backgrounds. And Nate also spent countless hours tweaking the various parameters of the RGB HIPS maps to make them look as pretty as possible. This was also just 20 square degrees, and it's a lot easier to optimize parameters for 20 square degrees and make that look nice than it is for 3,000 square degrees. And the mission for DP2 is to make as scientifically useful coad as possible with the same configuration over 3,000 square degrees. Okay, so what happened with the backgrounds for DP2? For Hypersub PrimeCam, they use a algorithm called sky correction task. And this works great. So on the left, you see the post ISR image, which Alex is going to tell you what ISR is in a bit. And on the right, you have a blink between two different background estimation algorithms. One is a per detector algorithm, and that's just a Chebyshev polynomial, and it subtracts off the small scale background before detection and measurement. And then there's also a full focal plane background estimate, which tries to capture the larger scale backgrounds. And you can see the outskirts of the stars are left in there. So we thought, okay, we can just tweak some config parameters and get this working for LSST cam. And sometimes it worked, but sometimes it failed catastrophically. And despite Lee and his low surface brightness science unit working on this for the period between going on sky in April and the pipeline freeze, which was December 3rd, it never got to the robustness that we needed to trust the coads that we were going to do shape measurements and photometry on. So the reasons for this was that so backgrounds need to account for any instrumental effects that aren't flat fielded. And the flats, there were still some residual offsets in detectors and effects coming out of the flats by December 3rd, by the pipeline freeze. And we are optimistic about this for DR1, and Eli has a plan that he's going to tell you about in about 5 minutes. So the original plan was to use the per visit backgrounds called SkyCore, like we do for Hypersub PrimeCam, and then construct a coad out of those, and then before doing detection and measurement on the coad, we subtract off a spline fit, but that background, the full focal plane background model, is still left in. It's still attached to the coad, and if you're interested in low surface brightness science, you can add that back in and get back to the pretty version with all the low surface brightness features. So because we did not use SkyCore for Deep Coad, what we did was after the DP2 processing, because we know that LSB science is very important for Rubin science, we made a second coad that we called Pretty Coad. And this was also we made this primarily also for the GRI HIPS map. So we only have Pretty Coads for GRI, and we attached the difference between the background and the Deep Coad and the Pretty Coad to the Deep Coad so that you can add it back into the Deep Coads when you grab them from the butler and get the pretty version. So this is not fully validated, but we thought it would be useful for you to have in your hands anyway. Please take a look at it and assess. I believe when I've poked around, it looks nice in some areas and less so in other areas, but the goal was to get data to you as fast as possible. So I'm going to hand off to Alex to talk about ISR, and for everybody who's going to be giving talks, please come up before write your question down, and we'll go through all of them at the end.
Thank you. Yeah, hello everyone. So my name is Alex. I'm a postdoc here at SLAC. And we're going to go through the key steps in the science pipelines. So click this button. I am going to be talking about instrument signature removal. So this is the first step in image processing that a raw image sees. It was a big challenge during DP2 for several reasons. One is the instrument complexity. Number two is the evolving conditions and cadence during the DP2 observations. The data volume, also hardware changes, coupled instrument effects, and the need for verification, provenance, and operational reproducibility of the calibration dataset. So for DP1, the ISR task of the pipeline was developed based on our best understanding of the physics of the detectors. And the goal is to reverse through that process in the photon transfer chain to undo all effects that aren't of astrophysical origin, or all parts of the image that are not of astrophysical origin. For DP2, we've refined this based on new hardware changes in the dome, and also for specifically LSST CAM. As Yusra mentioned, we have this timeline of the DP2 observations. During this timeline, we had changed the operational mode of the camera a few times, and also a few restarts. Every time things like that happen, we have to take all new calibrations. And so there are 3 different calibration epochs within DP2. So here's a long bullet point list of some of the main algorithmic improvements that we made in DP2. At the top, we improved fitting of the photon transfer curve. This is what we use to calibrate the gain, the noise that we use for variance plane estimation, and also how we estimate the saturation point of sensors. We've also, thanks to new dome or calibration system upgrades in the dome, we've updated crosstalk matrices. We also now have improved defect finding thanks to Agnes that can better capture the myriad defects that we have in the LSST camera. We've also completely updated the brighter fatter correction. We're now using this ASTIA 2023 correction, which is actually based on the electrostatic physics of the detector. We have shown that we're reaching year 10 level requirements on the PSF because of this. So in addition, we are better handling the mask plane. We've also have an entirely new flat field pipeline. We have 2 LEDs per filter that we use to illuminate the flat field screen in the dome. This allows us to build what we call anaglyph flats, which are sort of like the 3D red-blue glasses you get. So we have, and we combine flats from each LED to build a flat with an approximately flat SED across the band. We have new masking. There are two different sensor types on the focal plane, and they have different types of artifacts near saturation. We've also made other significant improvements to CTI measurement and also the improved daily tracking of instrument performance. I want to give two quick highlights on some major changes that might be interesting to you. So one, title's a bit clipped, but this thing we call our amp offsets. So we had noticed in photometric calibration some residual amplifier offsets. We also noticed in the PSF residuals and very early processings of small pieces of data. We have now had to turn on this amp offset correction to flatten images. These are small corrections to the image to flatten it. It's not the most principled approach, but we haven't seen any downstream issues with it. Secondly, also is this flat fielding thing I mentioned. So here's some pictures of the calibration screen in the dome. So the flat field algorithm pipeline was improved based on better camera temperature control and improved stabilization of the position of the calibration screen and the telescope. Yeah, we also have now new LEDs, so which allows us to extend all the way to the reddest part of wideband. So thank you. With that, I'll pass it on to Eli.
Let's see, how do I go backwards one? Did you just take the... All right, we want to go back to the flats moment. And I mean, the flat fielding is difficult with Ellis's TCAM and all of our different detectors. It's also difficult with this monitor here. I don't know the different colors. It's driving me bonkers. I need to have some calibration people in here. So, this is looking at the G band through two different LEDs, and you can see all of the detectors have different colors. If you've seen a picture of the focal plane, there's different shades of blue that you're looking in the G band. Now, the reason that SkyCore was having so much trouble is that, yes, we can combine these and we can get the chromatic response on average, but the color of the sky changes significantly over night, season, moon, no moon, twilight, and it really messes, especially with the E2V ITL break there. The SkyCore task just couldn't handle that. So I've developed a method to actually combine these on a per image basis that will greatly improve how it looks. Don't ask me about the U-band. So the photometric calibration, continuing on from how we've been doing it on DP1, the forward global calibration model. We have input was almost 30,000 visits and 6 filters, 55 million stars with 380 million observations. And the dense regions were downsampled. We don't need millions of stars like that. But of course, the ocean of stars image was a key part of how we were commissioning the calibration. About 70% of the visits were determined to be photometric, and full band coverage in DP2 was kind of spotty. The calibration regions with only a couple of bands is less well constrained. These will not, many of these are not in the coads. There's that big region that are in the single frame and not in the coads. But something that we have discovered at the end, and I'm sad about this, it's up to about 1% of our individual detectors have incorrect 0 points. And I used configurations that worked for DS and HSC, but the cloud structure in LSST is larger, and the code was not handling this well. And so for non-photometric exposures, it was trying to do interpolations that were just basically failing. And I think in the galactic plane as well, partly because of association and astrometry challenges there as well. So we have illumination corrections. These are basically the difference between background flattened and photometrically flattened images. In DP1, we split these out separately. In DP2, they were actually just internal to FGCM, and DR1, they'll be split out again. This is a little map of the in G and R band of the illumination corrections, and you can see there are rafts here, and the reason you see those is part of our preliminary instrument model. So these are residuals that are getting kind of put in there at a very small level, but they come out in the end. In the end, the repeatability measured with 10% reserved stars for signal to noise greater than 200. Each of these histograms is, let's see if I can get the mouse. Nope, I can't control it. I'm looking backwards. This is all stars, 25% bluest, middle 50%, and 25% reddest in that band. And then the sigma total, a few millimags, is the repeatability in the whole histogram. That is, of course, less than kind of the photometric error for the signal to noise 200 stars. So the intrinsic photometric calibration is somewhere below there, 1 to 2 millimags. Part of the, I meant to swap these, and I'm going to go forward, but there is a little thing hiding in there. There is a systematic error floor. This is calibrated out. We are not currently adding this to any of our errors. This is not propagated on. This is me telling you and going into the known issues. Don't trust anything below 1 to 3 millimags on the errors. If it's quoted there, there is a floor that you want to add. And this is for the single frame. For the coads, the systematic error floor is actually probably larger because of things that have been processing that's been done. And so the last thing I wanted to show, the throughput loss over time. Over 250 days of DP2, there's actually no significant loss. On the left, I have HSC, and this is just looking at reference stars, whole pool of reference stars minus instrumental magnitude. So this is just 2.5 log-based counts, log base 10 of counts. And it fades over time. And on the right, if you can see that, this is only 0.7 years in DP2, but there's no significant loss in the G band, even though even over that course from HSC would have expected that. But HSC, Blanco, Magellan, other telescopes that have very similar functions like this, they were aluminum, and the molecular degradation of the aluminum causes the loss in reflectivity. Even if you try to clean it, it's just going to go, and it's a chromatic change. But we have this triple silver on M1, M2, M3 with this magical overcoat, and it is phenomenal. I'm very excited about this. So on to the next.
Alrighty, I think
Yes.
this is me. So we've been promising cell-based coads for a long time, and with DP2, we're finally delivering them. And what I mean by cell-based coads is that we are, whether a particular visit contributes to a coad is decided mostly one cell at a time. The cell is 150 by 150 pixels. So either that cell goes into the coad or none of it does. And that's especially true for the chip gaps. And so if a detector doesn't fully overlap that cell, you don't add anything from that cell. What this does is it makes the coad's properties more consistent within a cell, but it makes those properties potentially discontinuous between cells. They're not necessarily discontinuous. You can have the exact same set of epics contributing to two neighboring cells, but we know that within a cell, there should not be discontinuities, mostly. The other big advantage is that the coad PSF, the effective PSF of the coad, is now much simpler to store and evaluate. This was a big bottleneck in our processing before because we had to essentially evaluate all the PSF models of all the input images at the right points and warp them to the right coordinate system and add them back together every single time we evaluated a coad PSF. And now we just store one PSF image per cell. And it's much, much more efficient. And it's also easier for us to ship something to users. They can like look in the FITS file and see what it is because it's just one image per cell. And that's a lot simpler than what we had before, which basically couldn't be reproduced without our code. Next slide, please. So the downside of this is that the measurement algorithms aren't fully leveraging the cell structure yet. They're evaluating the PSFs in sort of as if it's a piecewise PSF, but they don't know about the cell boundaries. And so if an object crosses the cell boundary, half of it could get modeled with the wrong PSF. We don't know if this, because we haven't gotten all the way there, we don't know if the cell coads are an overall net positive or net negative. We didn't see a big change in any of our metrics switching to them. So we don't think it's a big issue either way. But the important thing from my perspective is that this is definitely better for the many visits future of the survey. In the past, we would have expected the PSF model in particular to become increasingly impossible to evaluate as we got more and more epics. So I did say mostly about how things go in. And so I want to pose this as a question. I'm not sure if it'll actually work for those of you for anyone to like shout out or reply, but if we were to actually do what I said and drop an entire visit cell combination, anytime any pixel in that visit cell is masked, what would be the problem? If you'll shout it out, maybe I'll hear you. If not, I'll just continue in a moment. Well, so the big problem we saw is that if you have a mask that is fixed on the sky, say, the center of a bright saturated star, then you get entire cells lost in those areas. And so, in fact, I played a little bit of a trick on you. If you look at this slide and the one right before, if we could blink those back and forth, one of those is the cell coad and the other one isn't. And if you look very, very closely, you can see what the difference is. And this is one of the points I want to make about cell coads. You don't see the cell structure unless you're really looking hard for it. And in this case, the only place I was able to spot it is in the core of that saturated star. You can see that what's left out is along cell boundaries in one case and not along cell boundaries in others. And so this gets back to my point about mostly. We do, whole cell inclusion or rejection for chip gaps and boundaries of detectors, but we don't do whole cell rejection of all of our mask planes because we would just lose too much area, especially in places where the masks are related to what's going on in the sky, not what's going on in the detector. And so we have mask planes to capture that. I won't go into more detail right now. So the other thing I'll say is that these coads right here that I'm showing on these slides you've seen, whether cell or not, are what we call pre-detection coads. If you go to the next slide, what we actually measure the object catalog on is this one. This is what a deep coad really looks like. This is in the M49 region. And you can see that it looks much flatter, but this poor, beautiful spiral galaxy has been absolutely destroyed by being over-subtracted. And almost everything else that's big or bright has been over-subtracted as well. If you could blink back and forth between this one and the previous one. And that's because after we combine all the images, these are the regular single detectors background subtracted images that get combined, as Yusra said. We do another round of background subtraction that uses an even smaller scale. And that makes things easier for the deblender because, if you look between this and the previous one, there's all these little guys in the neighborhood of the big spiral that were over subtracted before, and they had a big pedestal that they have to deal with one way or another. And this small scale background fixes that. So it makes the job of measuring small things much, much easier. But it does wreck these big things. So if you prefer the big things, you can load the coad like this, and you can say, remove that final background will be subtracted from the coads. But you might want to do even more than that, and this gets back to the pretty coads that Yusra mentioned earlier. If you could go to the next slide. This is what it looks like if you instead of unapplying the background, the deep coad subtraction, if you instead apply the pretty background subtraction and switch to the background subtraction of the pretty coads, things look much better, at least to the eye. all these big things go out as far as they realistically do. That makes it really hard to deal with them with their neighbors, which is another reason why we don't want to measure on these, at least not right now. We have to have much more sophisticated deblending and measurement to deal with backgrounds that look like this. But this is more like what the true sky really looks like. If you're interested in low surface brightness things or big things, this is probably what you want to focus on. But I do want to emphasize, in addition to Usual's point about we don't trust sky correction everywhere, we built the pretty coads completely distinctly from the deep coads. We had different background subtraction on the visit images before we combined them. And the way I made this image was by differencing the deep coad and the pretty coad and fitting that difference as if it was a background model, a spline with on 64 by 64 pixel cells. And that mostly works pretty well because most of what it soaks up is the difference in those backgrounds. But if you had something that wasn't related to the backgrounds because, say, one image got included in the pretty coads and it didn't get included in the deep coads or vice versa, that would also get soaked up in the difference. If you had, a bright star that was transient and that all was in one of those missing visits in one side and not the other, that would also get soaked up here. And so there's lots of ways that this difference could go bad in addition to the sky correction going bad. So I think the pretty coad difference here that we're shipping is hopefully useful for a lot of things, but it really is not something we have validated thoroughly. And it's highly experimental how we came about it and kind of pulled it off at the last minute in the hopes it would be useful. So please, use with caution, but I hope it is useful. All right, next slide, please. I'm going to talk a bit now about what we do on top of those coads. And the first step there after we detect is deblend. And we've long had a lot of trouble with crowded fields. Those troubles are not over yet. I think overall in DP2 we've done a much better job of dealing with crowded fields early in the processing so we can actually build the coads, and we've improved where we can process the coads, but we haven't gotten as far as we'd like. So the big improvement in the crowded field processing and the deblending is here. So this is a 47 tuck from ComCam DP1. You can see this is just on the outskirts of the 47 tuck. So it's pretty deep, dense, but not nearly as dense as it gets in the end. The core of 47 tuck is an order of magnitude denser than this. But we still couldn't handle this before in DP1. So if you go to the next slide. So these are all red. Red means skipped blends. So what we do now is we deconvolve, not for our final deblending, but to initialize the deblender. So we deconvolve to not all the way, but to a well-sampled Gaussian. And what this does is it makes a lot of objects that were only blended because the PSF smushed them together. They become not blended anymore. And so now it subdivides each of our blends into smaller units that we can usually process. And in these crowded fields where everything got blended together, it actually subdivides them small enough typically that we can handle them as discrete chunks. It makes things faster and it improves the chi-squared. It's just all around a better deblending than we had before. So if you go to the next slide, we can see how this works. So this is a DP2 patch. It's not the same 47 tuck we saw before. I don't think it is, but it's if you go to the next slide, you can now see blink back and forth the before and after that algorithmic change. Before everything was blended together, and here we still have some chunks that are all big blends, but they're actually small enough that the blender can actually go after them. And in this patch, everything was handled. This isn't true everywhere. Basically, we push the part of the sky that we can handle, down closer to the plane, but not as far as we'd like in the end. In addition to those improvements for crowded fields, we have a new data structure that we produced that lets you go back and really see what the deblender did. We didn't quite publish all the information that you needed to reconstruct the deblender in DP1, and I think we are doing that now. And that includes the isolated sources that we didn't even have to deblend. So yeah, we're not all the way there. And if you go to the next slide, you can kind of see, or 2 slides away now, where we are in the sky. So the skip peaks is the main metric of, did the deblender fall over and give up because things were too crowded? And you can see that we're not all the way there yet, but we're making progress. Unfortunately, I don't have the same kind of plot for DP1 because DP1 didn't have all this data. But we are doing a lot better than we were before. But again, not nearly where we hope to be for DR1. Next slide, please. So we do have a lot of ideas, as I'm sure anyone here who's interested in crowded fields has ideas as well about how to do this better. Traditional crowded field codes subtract stars and work iteratively. We're hoping to not go straight to to only running a traditional crowded field code, but subtracting stars in the same sort of way is an obvious move to take, and we're going to explore that. And doing that hierarchically, so you start with the brightest things and you move down, or start hierarchically in a spatial sense, you start with the bend image and then move back out to original pixel scale, are both ideas we're thinking about. And we've also thought about a more brute force approach that might work for large objects, where we just subdivide into smaller cells and don't worry as much about objects that are large enough to cross multiple cells that overlap. We've also been using this Scarlet Light deblender for a while now on the COAD, and we have a much older deblender still in use on the single visit images. And we'd like to explore using the Scarlet Light on the visit images, both to get better source catalogs and to just simplify a lot of what's going on in the single visit processing. The single visit processing is much more robust in crowded fields now, but it came at the cost of a fair amount of complexity, and we'd like to simplify that by using a better deblender. All right, next slide. So in terms of other things that have changed in what we're doing on the COADs after we deblend, back with DP1, we started running our multi-profit Galaxy Forward modeling code. This is Dan Toronto's effort. Apologies to Dan for not getting his name and picture on the slide. I should have done that. An adjustment there is we're now running a multi-band exponential fit first to initialize the Surstich model fit, and that helps deal with the perennial problem of objects that are both too big and too bright, or measured to be too big and too bright. We now have some errors reported on the Surstich and exponential fits, and some of that's actually quite hard to do in terms of coordinate transforms and making sure that that the distributions stay valid under coordinate transforms. And so we're still working on that. But we also, and I'm actually very excited about this and seeing how well the science community likes it. We've long had this classification extendedness that was a really crude magnitude difference between the C model fluxes and the PSF fluxes. We now have something similar that's not just a binary either or, and that's measured on all the bands at once from these multi-band Surstich fits, called the model extendedness. And I'm hoping that will work better for a lot of people for star galaxy classification. It's certainly something that, not being binary, you can choose where you want to be on the completeness purity curve, and hopefully get better results. Next slide, please. All right, finally, at least for me, we are now producing the meta detection shear object table. And this means we are running a state-of-the-art self-calibrating weak lensing shear estimation code meta detection. Developed, I think initially for DES by people who are close collaborators of ours in the dark energy science collaboration. This produces the shear object table. Just because we're running their state-of-the-art code doesn't mean we've done it correctly. There's a lot of work that needs to be done adapting a shear estimation code to a new data set. And I think we've done a pretty decent job, but I'm sure that there will be problems discovered. And our goal is to fix those problems before we get to DR1. And hopefully, because the requirements for DP2 weak lensing science are not nearly as stringent as what we would need for DR1. Hopefully, we've done well enough for DP2 science to do this and do this well. One key caveat on this is that you should not be matching the shear object table to object, or really to anything else. Part of what makes it a state-of-the-art measurement is that it corrects for detection biases. One of the awful things about shear is that it biases everything you do, including exactly how you detect objects. And the way this works around that is by doing its own self-calibration of what it detects. And if you match that to anything else, you end up filtering your catalog based on a different catalog's possibly biased detections. So you can't get away with matching shear object to anything else. And instead, shear object includes some photometric measurements of its own. And so if you're doing weak lensing or other cosmology studies, and you need to use shear object, you need to be very careful how you get other quantities that you want to relate to those objects. I think that's it for me. Next slide and next speaker.
All right, I will talk to you a little bit about the image differencing and the changes again from DP1, and also some changes from DP2 to what is in the alerts now. First off, So I wanted to characterize our completeness so far. This is work done by Bruno Sanchez in the data from February 24th when we are releasing our first alerts. He injected fake sources. Just a demonstration of that here. This is a case where we are injecting on a hosted fake source, and so we have the hosted and hostless for different types of transients. In these cases, we are getting about 98% completeness. We think we know some of the various ways that we can improve that in the future. Looking at these injected fake sources as ways of further assessing our performance, we are recovering the injected magnitudes very well. The one caveat I will give here is that in one of the fields, we were seeing about a 15 millimag offset. Still investigating exactly why that was showing up in one field. We'll work on that. I wanted to now talk about some of the major changes in difference imaging from DP2. There are a few key features that I wanted to highlight here. One is these glint trails. Here I have highlighted some satellite debris that is showing up as an inconsistent trail across one image. Now we are using some of the code developed in Solar System in order to identify these linear features and at least flag them. In the DiaSource catalog, there will be a glint trail column, and that can tell you if the source you're looking at is likely contaminated by one of these debris trails. We also have added cosmic ray detection and masking on difference images. This was coming up from cosmic rays that crossed a static source. And so we're either not being flagged or we're being masked only incompletely. And then in the difference image, when the static source is removed, the cosmic ray fragment would come up. This is thanks to our brokers for having noticed this in our early alerts from before they were public. And that has allowed us to quickly identify, easy to run. That's not an additional step that's done in difference imaging now. And a final one that I wanted to highlight, and I'll talk a little bit more about, are the diffraction spike masks. So first, you're highlighting that glint trail, and then also around our bright stars, you see these diffraction spikes. Masking out the diffraction spike has a few benefits. It also does introduce some new complications. The benefits is we're no longer detecting on the artifacts around bright stars, but unfortunately, it also means that the cores of these bright stars are now missing, especially in the coads. And depending on the types of recovery that you might be trying to do, that does have an impact on the science. Point out these images here put together by Dan, who is in the other session right now. So showing some of the differences in detections here. Previously, we would end up with a very large number of spurious detections around bright stars. With the spike mask in place, that is greatly reduced, but as you can see, we still have a few detections around the edges of these mask areas. Here we are getting one detection in the center because this is from multiple bands, and in U band, the star was not saturated. So the measurements of bright stars will frequently come from U band, which is being the only band that might not have been masked out in those cases. The pretty coads, HIPS maps, will include that do not include the spike mask. And so that is one place that you can go to in order to try to recover what the source would look like without this masking. Another feature that has been introduced, which was introduced primarily to deal with some pedestals in U band, where you're getting spurious detections, but also, as is highlighted here, more spurious sources around the wings of bright stars, and it is an additional step of background subtraction in image differencing. In image differencing, we are looking primarily for very point-like sources, and we don't have the same concerns about preserving galaxy structure. And so I have implemented a far more aggressive form of background subtraction for the detection step so that we can filter out anything that looks like a pedestal region or otherwise, and that removes this whole cloud of detected region around this bright star and similar places. And now that looks very flat. A final feature that I want to talk about in image differencing is an issue that exists in DP2. And what I'm showing here is the prototype, which will be in the stack by the time we are back on Sky. So this is coming soon to the alert stream, is image difference deblending. Showing here an example case where what we would have previously, two sources close together, one subtraction artifact, here a variable star that was negative in the difference image because it was dimmer than in the template. And because they were close together, they were merged into one, and the detection was on the artifact, and so we lost the variable star. With the deblending, these get separated into two different footprints, and now this blue X is marking that is now recovered, measured, and even has a 1.0 reliability score. So is successfully recovered and continued. On the far side there is what the science image looks like in this case. You'll note that each of these little pluses here is marking where the actual peaks are. So that is what we are trying to make sure that we do not deblend too much, because we don't want all of those peaks to turn into a bunch of spurious sources that will contaminate the alert stream and contaminate our database. Refinement of that is the last step that I'm working on before this is now in production and in the alerts. And that's it for me.
Hello, I'm Tatiana Acero Cuellar. I'm a PhD candidate at the University of Delaware, and I'm going to talk about the real bogus model. So the model is still the same architecture, but very light CNN. The input are the VC difference and template stamps, and the output is the reliability score. So this past year, we introduced a few things. So the first one, we introduced the reliability version, so we all can communicate very easy about which model exactly. So the 0.1 was introduced last year and was deployed for DP1 and DP2 data. The 0.2 was introduced this year and was used for the initial alerts. And the 0.3 was very recently introduced, and it's being used also for the alerts. So this is a summary of the versions. So from the 0.1, we fine-tuned the model using LSST-CAM data with Zooniverse labels. I will explain that in a moment, to create the 0.2 version. And then also starting from the 0.1, we fine-tuned to create the 0.3 using the ComCam fakes and LSST-CAM data with Zooniverse labels. So the data with Zooniverse labels, it's a data set that we were able to create thanks to a bunch of labels made by citizen scientists via a Zooniverse project. Yeah. So another thing very important for the alerts is the reliability cutoff. So for the current version, the 0.3, the cutoff is at 0.5. So that means that any DI source with a score below 0.5 is not making through the alert stream. So the goal is to have a model that is more confident about the bogus, so that threshold can be moved a little bit closer to 0. Okay, so the performance for the current model, given the data set that we use for training and testing, we satisfy the requirements, performance, purity above 95% and completeness above 90%. Okay, so current and future work, the performance on the variable objects is still not so good, but it's better than when it was the 0.1 model. So the Zooniverse project is currently on pause while we're still discussing what is the best way to approach with the project. But in the meantime, we are collecting data with a more local group of students at UPenn. We are for sure going to use LSST-CAM fakes And all of this information and more is available in this deck note.
Hello, I'm Jake Kurlander. I'm going to be talking about the solar system pipelines. I think last year there wasn't a solar system pipeline, so the difference is all of this. First, the exciting stuff, discoveries. Everyone loves new asteroids. So pre-DP2, we did not have difference images, and asteroid discovery is generally supposed to be run on difference images. But some folks, Matt and Kevin at Harvard and Ari at UW, performed some magic and managed to do difference imaging without difference images, or at least catalog differencing, which got us a really reduced source density, and we could search for asteroids pretty well without templates. So looking at the DP2 data before DP2, without templates, we found 11,000 new asteroids. This was awesome, super exciting. Then DP2 occurred and we researched the same, we performed an additional search in the same data with the diffims instead of with our transient catalogs, and found an additional 22,000 asteroids. So the big picture moving forward is we can do asteroid discovery at a smaller scale without templates, but we can do a lot more asteroid discovery when we do it with templates. Difference. So we're currently at about 35,000 new Rubin discoveries. Of these, by far the coolest part are the 1,400 trans-Neptunian objects. This is a much larger fraction of the outer solar system that we've discovered than the corresponding inner solar system objects that we've discovered. Here's a orbital plot of the candidates. These are, again, mostly by Matt and Kevin from Harvard. And 1,400 TNOs is something like a quarter of the Kuiper belt that's known right now. So in the last year, Rubin's discovered something like 25% of all Kuiper belt objects, which is pretty darn cool. That's something like double the next largest TNO survey. So good, really good, Matt and Kevin. All right, those are the discoveries. Now let's talk about the data that's available to you in Data Preview 2. Rubin has really good photometry and astrometry, as folks have and will describe. Over here is how we do association. So this circle is a 1 arcsecond circle. I know it looks like a very big arcsecond, but I promise you, this is 1 arcsecond circle. And we have a heat map of where, relative to the ephemeris position. So the ephemeris position of an asteroid is at 0, 0, center of that black cross. And that's a heat map of where we see asteroids relative to where we expect them. So in general, asteroids are right where we expect them. We have very good photometry. We have very good astrometry. DP2 includes 300,000 objects that are measured at least once, and 8.1 million measurements of solar system objects. All of these associations between a dia source and the expected position of an asteroid are made with this flat 1 arcsecond circle. So although you don't see a lot of density over here, there are some SS sources with ephemeris offsets of around an arcsecond. And so although we didn't make many cuts on which SS sources we put into DP2, I would stress that anyone using this for science should take into account the fact that nearly all of the SS sources have very, very good ephemeris offsets. So if you have a data set for one object that has 6 detections, and 5 of them have ephemeris offsets of less than 1/10 of an arcsecond, one of them has ephemeris offset way over to the side, maybe throw out that one. We also didn't cut on reliability, on positive PSF flux, on the expected magnitude of the asteroid being like the measured magnitude of the asteroid, on the source looking like an asteroid. So if you're using this for science, do look at the data and make sure that you make some sanity cuts on your own, on the data that you're using. Similar warning for the SS objects. So there are some solar system objects that have been measured hundreds of times in DP2, and that is really, really fantastic. There's some solar system objects that have been measured a couple of times in DP2. That's also fantastic. But any assumptions you make about the shape of the data, if you are hoping that like the asteroid, okay, asteroids are variable. They aren't perfect spheres, and so their light curves change over time. And if there are a bunch of objects that are like measured all in the R band for a while, and then there's a gap, and then all in the G band. And if you want the color of this asteroid and its magnitude is changing with time, the change in magnitude over time might mess with the cadence, and you can end up with some weird colors. So again, look at your data, try to think about what the asteroid could have been doing over the period of time it was measured, and yeah, we've got a really great cadence for the survey, but the DP2 cadence is non-uniform and doesn't necessarily constrain individual objects perfectly. All right, then let's zoom in on this astrometric offset plot for what most of the what a lot of the solar system team was doing for a lot of last year. So if you zoom really, really far in, you find that the cross is not quite in the center of the yellow hill. So solar system folks got a little worried about this, seeing it May, June of last year. We started really digging into what's going on here. So we're seeing asteroids not quite lined up with the ephemeris position from the orbit catalogs. And we started complaining to the pipelines folks, talking about astrometry, but breaking the offset down over the sky, we saw a pretty strong spatial structure. So we're seeing asteroids typically south about 20 milliarc seconds, which 20 milliarc seconds is tiny, a tenth of a pixel. So this is really, you can only do this in the statistics. Often pretty far south, but over here, more west of where we expect them. And this got the attention of the astrometry folks, and that's the transition.
Claire double checked everything. She found no evidence of a 20 milliarc second offset in the astrometry. The mean offset with Gaia DR3 was within 1 or 2 milliarc seconds for the stars in DP2. And the solar system science unit went and looked at just the asteroids that had orbits that were constrained by observations in the Gaia data and found that offset did disappear. The 20 milliarc second offset did disappear. So what that means is that Rubin has uncovered a genuine systematic offset in the pre-Rubin existing orbits. The solar system science unit has some hypotheses on why this might be. They range from things like observations from the north are different from observations from the south. If you have any ideas, Jake and Mario would love to hear them during the break. But the astrometry is great. What's new for DP2 astrometry is that we released a isolated star stellar motions table, which has proper motion and parallax for all the stars that went into the astrometric fit. And then also now astrometric calibration is a two-step process. We still use GBDES, the astrometric calibration algorithm from DES and Gary Bernstein, but on top of it, we fit the per visit residuals with a Gaussian process model to fit the atmospheric turbulence. And this brings down the average repeatability of positions from by 5 milliarc seconds, which is huge. This was a huge contribution. So our median repeatability in the separations of stars now is 7 milliarc seconds. And for most of the sky, we are below the design goal of 10 milliarc seconds. But of course, we can always do better. For DR1, we're planning on counting for differential chromatic refraction. We're also planning to account for the small scale structure in the camera. So if you bin the residuals by direction in X or direction Y, and if you bin them by position in the focal plane, you can see you can see structure from the chips themselves in their height, and we can model this and add it to the astrometric bit as well. Okay. So to wrap up, the pipelines are performing well for DP2, but we can always do better. We are committed to tracking the state of the art in algorithms all through operations. All through construction, we've been monitoring what people have been doing and trying to incorporate new ideas into the algorithms, and we plan to do the same all through operations as well. Our goal for this last year was to get data products in your hands as fast as possible. What this often meant was that we had to make a decision and just keep going. Skycore wasn't behaving like we expected, and we couldn't get it right. Gotta move on. In order to get the data out to you by today, we had to just keep moving. So the goal of this was that if we got the data into your hands earlier, we could start getting feedback from you earlier. It's always better to have more eyeballs on the data. We welcome your feedback. We welcome your ideas. If you have ideas for fast and robust algorithms that will improve things, we want to hear them. Community is the best place to post like some weird thing you saw in the data, and the more details you can provide on that, the better. Still working on the paper. Please cite PSTN 19. We have a DOI for it. And this is not a pipelines event, but there are coincidentally 2 EDP2 hack weeks being held August 17th, the week of August 17th at both UW and Princeton. I've met a lot of people here from universities in the Mid-Atlantic. Please swing by Princeton any day that week, and you'll get to hack on the EDP2 dataset alongside the folks that made it. Thank you. Okay. So to submit a question, you can either use the QR code or go to slido.com and enter in this number. So what we're going to do is wait for some questions to roll in, and then if anybody wants to answer them, please raise your hand either in the room or on Zoom, and we'll answer questions.
I see a question about fringing. So in the Z-band, we see fringing in our flats, but not on sky. I don't understand this. But any fringing that you see on sky is imparted by the flats, which is bad. So we were not considering this, and we don't have code yet to remove it from the flats, and we also don't know why it's there. We finally had the fiber spectrograph working, and we had scheduled to take fiber spectrograph observations of the LEDs. Do they look like what we think they are? And then the terrible storm came. So I don't have answers there. Y-band has weird surface effects that aren't quite fringing. There's other taller poles, but so we don't have any fringe correction at the moment.
So the second question, I guess, how do the completeness numbers on slide 68 compare to those for version 0.2. So I don't have the numbers at the top of my head, but the difference between the 0.2 and 0.3 on the real data was not very significant. The difference was more important for the for the fakes because the 0.2 didn't include the fakes. So the 0.2 model was very biased against a low signal to noise ratio. So that's why the 0.2 have a very short life.
Is Chris there to expand on his question about co-ed backgrounds?
Yeah, I didn't know if I was allowed to talk. Okay, so sorry, I wanted to use sound waves and not type. All right, so really great talk. So I had a hard time understanding when you were talking about the co-ed backgrounds and the pretty co-eds. So just generally, like basically, I think I don't understand. So we start with a bunch of single images and we do background subtraction on them, and then we warp them and we co-ed them together. So is the idea that there's some background that's left over that adds up, and it's how you deal with that? Could you sort of talk about generically what's going on, and then what the differences between those two pretty and co-ed?
Yeah, so the key difference, what you just said, we start with visit images and we warp them, we co-ed. Sorry, we start with visit images, we background subtract them, we warp them, we co-ed them. The key point is that actually happens twice. We have the visit images, we background subtract them one way, we warp them, we co-ed them, that makes deep co-ed. We background subtract them a different way that's generally more conservative and doesn't subtract as much stuff or subtracts only on larger scales. We warp those, we co-ed those, and that's how you get pretty co-ed. And then in order to ship pretty co-ed, we instead of giving you the pretty co-ed images directly, because that's a whole nother co-ed with a whole bunch of pixels, we figure, well, these should mostly only differ in what their backgrounds are. So we diff those images and fit a background model to the difference between those images, because assuming that difference is mostly just background, but it's the co-added differences of a bunch of different per visit background models. And then we save that background model so you can restore it. Does that help?
I see someone has suggested that the plot of astrometric shifts on the solar system objects when spread out in those 5-degree red bins on the sky look like the map of proper motion visits from Gaia. Are Gaia positions corrected for proper motion to the epoch of the visit? So yes, Rubin does correct the astrometric catalog according to proper motions to the epoch of the visit, and there were various times when solar system people might have said we think it doesn't, and now we are very, very sure it does. But I would pose a question about what might happen if Northern Hemisphere telescopes didn't correct their astrometric catalogs for Gaia proper motions, then took astrometric measurements of asteroids, submitted them to the Minor Planet Center, and the orbits were fit only to unproper motion corrected catalogs in the Northern Hemisphere. And I'm not going to name any names, but I've talked to some folks at some other observatories and asked them to make versions of our plots. And it does look a whole lot like this analytical offset that Ari Hines computed for what it should look like as a function of RA if you don't do that. Mario's got his hand up. Okay.
Sorry. It could be a part of it, but the problem is that people started using Gaia since about 2017, 2018, and we're actually seeing things get better after they have. And the problems are more on asteroids that have observations before Gaia started being used. So I think you're right. People don't propagate as a matter of course, but it's probably not the whole story.
So the question about the data quality metrics, those we certainly produce those as tables. I do not think that they are included in the DP2 release in any form right now. Because we haven't done the final DP2 release, that might be something we could consider, but it's not something we had really put in our plans for releasing.
So for
So there are, I'm sorry, Jim, I may have misunderstood what you said. Isn't this a question about the visit summaries partly? The second question?
There are some data quality metrics in the visit summaries and the visit detector table that we absolutely do ship, and those are part of DP2. There
Right.
are
So
other things that are more like what I thought that the viewer was displaying that I don't think we have in a public table right now.
yeah, so okay, good. That's what I thought. So just to recap, so visit summaries are part of early DP2 and they're stored in the Butler. If you go to the dp2.lsst.io, you will get more information on them. And there is on the list, I know I keep saying this, but on the list is exposing more metadata about the observations and the data reduction searchable tables going down the road. Once we've shipped data, we'll switch over to shipping metadata. But I think the visit summaries as they are right now still have useful information in them.
I think that's right, but I think there's actually very little in visit summary that isn't already in visit detector. And visit detector, because it's in TAP, is a much easier thing to access.
Yeah, I'll just add that this is all coming from like a big JSON blob that gets displayed live. And so like there is more information here. I think we need to go think for a little bit about just the right way to just that sort of handful of tables that go into making this, but I don't think it should be fundamentally hard for us to make that happen.
repeatability before FGCM, it's larger. It's still going to be better than 1%. And that's my expectation. I looked at this ages ago.
We have the QA plots for that, and if you find us during one of the breaks, we'll show you the before and after FGCM of the photometric repeatability.
And also that is what before FGCM number is what I would accept for prompt right now. In the long run, because we'll have templates and reference catalogs built from our own data, prompt should get better and get closer to FGCM because it's one new image on top of a whole bunch of FGCM's reference catalog that goes very deep. But that's not where we're at right now.
Okay, we are all out of questions. Thank you all for coming, and thank you all for the pipelines people for presenting and all the hard work this year, improving our algorithms.